Hello, everyone. I'm extremely excited for you to join me on this new series. My name is Martin. I will be your instructor and I will teach you from zero to hero, from the very basics of AI towards what I would call complete functional AI literacy. And what I mean by that is that I don't want you to go into the deep mathematics or deep maths or advanced equations of AI or understanding how it works at a very granular level. I want you to be very functional with it. I also don't want you to be completely lost. I know many of you are in business. I know many of you, your companies or your work or your college or your high school, your middle school, or whatever you do, your personal time, you've been in contact with AI. We see a lot in the news, a lot of doom and gloom, people saying it's going to replace us all, it's going to render us all jobless, right? Some companies are using to justify layoffs, and there's also the other end, right? The hypers, people saying that AI is so amazing and it's working so well for them, and for you it doesn't seem that it works. So the audience for this course is everyone, really. But if I had to choose someone, it would be someone that their days of studying has long passed, or for some reason, at least studying maths or anything related to AI or computer programming, more AI specifically, have passed. And they are in contact with AI. They're a bit fearful because they don't understand and it seems to know what they're doing. And they really just want to improve themselves, be more up to date, and basically become knowledgeable on this new emerging field, which I think is very, very exciting. It's probably, for me, I would like to compare it to the internet in the early 2000s, right? We are going to discover the possibilities as it goes. And humanity, I would say, will evolve with this technology. And I really hope this video, which I'm giving you for free, I have a master's in AI. I've been working with AI for over 7 years, and I work with AI professionally. So that's my day job, is working with AI. And for me, I will give you this for free. Everything I know in a condensed form. You won't have to do my master's, or you won't have to have my years of experience to know what I know. At least what I, again, would say a functional level. And I hope you find it very useful. So these videos might seem they're unrelated on the topics that I'm gonna cover. I would recommend you highly. Of course, you can choose whatever video you prefer, but that you follow them in order, and that you trust the process. You trust that I've picked an order that will eventually tie everything together, even if perhaps the first few videos don't seem to connect with each other. So without further ado, let's start. And the topic of today is binary numbers and ones and zeros. And for me, this is a very important topic to start demystifying how AI works, how LM works, how your ChatGPT works. Because a lot of people will say, oh, it's just rocks, right? We've made this out of rocks. Or it's just ones and zeros. It's nothing more than that. But it's very abstract. Up to quite recently, I would say, it was not very clear to me how this all connected. Okay, sure, they're rocks, but how? You know? And I feel like this is a very important topic to cover because I think it's not that hard to understand. So, for those technical people, just a disclaimer, I will take some, what I would like to call, artistic or educational shortcuts, where I will perhaps not go in technical detail and stuff, or take some liberties which are not 100% correct. They give the main point across, which really is the goal. I don't expect anyone to be an expert. I don't expect them to be functional and what I would like to call literate. So in the future, you'll be able to think critically on AI, make your own decisions, understand which model does what, the cost benefit, and how to prompt better and how they work, and not feel afraid of them or not overhype them. Have a realistic take on how they work. Without further ado, let's start. Binary numbers, perhaps some of you have seen them, they just seem to be a bunch of ones and zeros coming together. And they don't make a lot of sense, and it's not very natural. They're for me personally, a bit ugly and a bit non-intuitive, but they're everywhere. In fact, you've probably seen that in your power supplies. When you go turn something on, you'll have a button kind of like this, one switch like this, where you would see to turn on and off. And this, I like to see it's a 1, but I like to imagine it as an electrical wire. And I like to imagine that there's a battery down here, and that when this battery is live, so when this battery is live, it's sending a current. So I should be careful. So for me, I like to imagine it like this. I like to imagine it that a 1 means it's live. So it's on, there's some electricity going on. And just very naturally, what for us is a 0. The 0, of course, represents nothing. It means the lights have turned off. There's no wire going on. It's safe to touch. So this is where I would like to start our lesson. Is I would like you to imagine that every time we see a 1, like here, this means on, right? There's a signal going on. And whenever we see a 0, like here, that this means off. And you can imagine just as turning on your light, just a battery here. And it's connecting to a light bulb. And let's say that I can pulse this light bulb. And I can pulse this light bulb every second. So every second, one time per second, I will have someone looking at my light bulb. And every second, I can turn it on or off. If we're seeing the light bulb every second, we can assume that over time, let's say in 10 seconds, I'll have 10 distinct values, right? So let's say I have my column here for time. And since I only have one light bulb, I just put light bulb number 1. And then we can say that at 1 second it was off. Then let's say at 2 seconds it was on. Then let's say at 3 seconds it was on again. And then at 4 seconds it was off. Just pulsating and making sure that whoever is checking the light bulb is checking it every second. With this notation in mind, let me just redraw it in a more clean way, my light bulb. So let's say this is my light bulb, and I have a line here, and let's say I have my eye here, looking at the values of my light bulb. Let's assume that here I have a massive battery powering my light bulb. We can agree here that light bulb number, I would call it light bulb number 0. So put a 0 here. We can agree that light bulb number 0 can now give us 2 different type of numbers. We can represent a 1, which means when it's on, and we can represent, of course, when it's off, always a 0. So these are the values for our light bulb number 0. Now let's get a bit more creative with here and expand it a bit. So let's add a second light bulb. Let's add light bulb number 1. And now our eyes are seeing both of them. They're seeing 1 time per second, right? Once a second. They're seeing both light bulbs at the same time. And now our light bulbs are doing something a bit different. I can have this light bulb number 1 being 0 or 1, and independently I can have light bulb 0 being 0 or 1. And now my eye will be able to see both of these values at the same time and make pairs. So for example, let's say we have our time here t. Let's say we have, just to keep the same order, we have our light bulb 1 and our light bulb 0. As time goes by, I can now represent 4 different pairs, right? They can all be both off. And let's say that this equals 0. I can have my new light bulb still off. And as we've discussed before, the old light bulb be 1. So we can have it like this. Since we already have 0 and 1, we need 2. So let's make our light bulb, when it's on, represent 2. So as time goes by, let's say my new light bulb goes on and my old light bulb goes off. And since I agreed that this one, when it's on, it's 2, we have a total value of 2. And let's say in the 4th second we turn all of them on. And now we have a value of 3, right? We have 1 here, which represents 1 plus 2. What you can realize here is that with a combination or with a light bulb, right, as a base, so let's call our light bulb our base, our light bulb only has 2 ways or 2 values that we can give it. It's a 1 or 0. Mathematically, the number of options that we have can be called a base. Since we are using a number system or a light bulb system that only has 2 options, we can assume that we're base 2. And it means that if I need to represent a number bigger than 2, since I only have 2 options, I have to add an extra house. I have to add an extra light bulb. This is very similar to our, what I would like to call normal numbers, which they're actually base 10, right? Why base 10? Because in the first house, we can have 0, 1, 2, 3, up to 9. 10 options. You have 0 plus 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 options, which represents our base. And as soon as we're out of options, or we arrive at 9, we have to make 10, right? We make a new house, 10. So how many options you have before you have to make a new house or a new slot or a new light bulb is called the base mathematically. And binary is base 2. And you can see that we can represent numbers by just turning them on and off and having something checking the values at a specific time, once a second or twice a second, because then we can have this combination of numbers meaning something. Remember when I told you that the order of the light bulbs matter? And as we go, jumping from one to the other, they gain value. We can use this mathematical trick since we know our base 2, and we can multiply against the position of the light bulb to know what value it is when it's on. So if we take light bulb number 0, there's a special mathematical property that all numbers times by 0 equals 1. So here, again, we know that since we've numbered our light bulbs, that light bulb number 0 is 1. Then we can get light bulb number 1. Light bulb number 1 is 2 because mathematically any number to the power of 1 is itself. So we go here, 2. And that's exactly that we saw that once our light bulb number 1 is on, it's 2. So what happens if we add light bulb number 2 here? Well, remember that our light bulb 0 represents 1 when it's on, or 0. Light bulb number 1 is double that. Right? You're doubling, so it represents 2 and 0. If we double one more time, because remember, if both of these here are on, we get 3. We have 4, which is the next number on the line. So that means that if light bulb number 2 is on, we have 4. And then our eye can look at them and add them all up. So 4 is doubling our previous light bulb. So 2 to the power of 2. Check here that we have our light bulb number. We can have that our light bulb 2 represents 4. And with this, you can start mix and matching your light bulbs and make any number you want up to, well, the easy way to do it is to turn all of them on, right? That's the max value we can have. So, and we can have here our light bulb 0, our light bulb 1, and our light bulb 2. And here we can start seeing what the values are on. So if all of them are off, I have nothing, right? So I have a 0. If I only turn on my first light bulb like this, then we agreed I have a 1. If I only turn on my middle light bulb, we agreed I had 2. If I turn on my middle light bulb and my first light bulb and keep the second new one off, we agreed we had 3. Now, if I just turn on my new light bulb and I turn the other ones off, I get 4. If I turn on my new light bulb and my oldest light bulb and leave the middle one off, I get 5. If I turn only my newest one and my middle one on, I get 6. And if I turn all of them on, I get 7. So out of 3 light bulbs, I've just made 8 possibilities, 8 different numbers. In computer talk, every light bulb is called a bit. If we have 3 light bulbs, this is a 3-bit value. And this is important to specify the bit because it tells our I how many numbers, right, how far left it has to consider. So for example, if we made an agreement to our I that we are only dealing with 3-bit, and we gave them a range of numbers like this, our I would section them off this first and then this, with this being 5. And I'll give you a moment to try to figure out what this value is. Got it? Good job. 6. And we can continue by adding more wires and light bulbs, making bigger and bigger numbers. If I added a 4th one, now what value would it be if I turned it on? Remember, we're doubling here. Remember, we're doubling here. So I'll give you a moment. Yeah, correct. It's 8. It's 8. Remember, we're doubling, and all of them are on. At least up to here, we get a 7. So we go on the next number. And what is the total numbers that we can support now? Well, let's see. What happens if we turn all of them on? We would have light bulb number 3, light bulb number 2, light bulb number 1, light bulb number 0. And if it's on, this is 1. If my second light bulb is on, we know it's 2. We know we're always doubling, so this is 4, and this is 8. And if we add them all up, 8 plus 4, that's 12, plus 2, that's 14, plus 1 equals 15. Whoops. So now that means that a 4-bit value can support a range of 0 to 15 or 16 numbers. As you can imagine, we need more than 16 numbers to use our computers. And now I have removed the light bulbs, and I'll just, hopefully you understand that a 1 and a 0, and we read them always from right to left, with always the first one being light bulb 0, and then we add them as we go left, that we can represent almost infinitely any number that we're used to. An important distinction before I proceed. Each light bulb is a bit. If we have one, two, 3, 4, 5, 6, 7, 8 light bulbs, that's an 8-bit value. That's what we called a byte. We're computer people, love making things confusing, so that's how it is. But it's very important that you don't get confused between a byte and a bit. Remember, a byte is always 8 light bulbs or 8 binary numbers or 8-bit stacked together. So how many values does an 8-bit number have? Let's calculate. So we know that here we have our light bulb number. So here we know also that we have a base 2. We only have 2 options, right, per house or per light bulb. We know for option number 0 we have a 1. We know for option or light bulb number 1 we have 2. Remember, we're doubling. We know for light bulb number 2 is 2 to the power of 2 is 4. And we can double it as it goes. 8, 16, 32, 64, and 128. And just again, hopefully you can see that the power of 2 is matching here the light bulb number, I'll still go ahead and fill out for you. Now last but not least, how many total values we have here? We have, I'll make it easy and fast for you, we have a range of 255 to 0, and that makes us 256 possible values. Now you might think, well, why do I need to know what a bit is? Of course, I've seen bytes in memory. But what's the point of knowing bits? Well, it's all around you, more than you think. So when you go install some software, perhaps you've noticed that it says, at least for Windows, sorry Mac users, 32-bit. And the more modern ones will say 64-bit. Just like that. So that means we have 32 light bulbs at once that our eye is processing. So you can see it's not a small number. I'll let you, as an exercise, calculate how many options that is. And you've also realized that on the newer architecture, we have 64-bit. If you do the maths, you'll see that is not double the capacity. It is many times over the capacity. Why is it important to know about bits? Well, another thing perhaps that you've noticed is hexadecimal numbers. And what they're saying is, hexa means 6, is that it's a base 16 number system. And just like I showed you with binary, it means that once you only have 16 options before you have to make a new house or a new slot. So if we start with slot number 1, it'll go 0 to 15, or at least in value, and then you have to put in another value, okay? And the reason for this is electrical engineers got tired of having to write all of these binary numbers to represent stuff. And just like all humans, they got a bit lazy. They decided to make a shorthand for 4-bit systems. If you remember correctly, when we have a binary number that has 4 bits, we can represent up to 15. If you don't remember the calculation, I'll do it for you. There you go. 15 when all the light bulbs are on. They got tired of stacking all these zeros and ones together, so they invented the hexadecimal. And the hexadecimal is not a complicated system. You have all of your standard numbers. And then to represent 10, 11, 12, 13, 14, and 15, they just added letters. So next time you see something like this, you know, 1, that's in hexadecimal, and 2, you will know that these numbers, they are just hexadecimal numbers which you can derive the value of. So I won't go in detail, but 14, and I'll let you also as an exercise to calculate what that is. And this is a memory address in your computer, and just like we have our normal addresses with a street number and a house number, your computer has memory addresses. So a number represents where in the world or in the city of our computer this piece of information lies. Now, coming back to the topic, I'm sure you're wondering, okay, how does this link to AI at all? Well, we can be very fancy with bits. We can change a bit the rules, and we can represent the system as we use in normal mathematics or in normal day-to-day, just using binary numbers. So, for example, what I could do is, let's go back to our 4-bit notation. So just as a reminder, this goes to 0 to 15. But let's add an extra bit here. we'll call this one the sign bit. And what it means is, for example, let's say that when it's 0, it means a positive number. And when it's on, it means a negative number. Now we've allowed ourselves to represent with 5 bits numbers ranging from minus 15 to 15. We can do a similar thing with decimal numbers. Let's take, for example, a 9-bit system. And let's say that the furthermost 4 bits, say something like this, these ones, let's say they are whole numbers. We have one special bit here in the middle, which we can say if it's on, it's a decimal point. And when it's off, it's not. So now, in the case that we have this bit being on, our next 4 bits here represent the decimal portion of our number. So for example, let's say they're all on. This 9-bit number now will represent, I want you to stop it and try it first. I'll give you a few seconds. Done. I hope you actually paused the video and did it, and you didn't skip the exercise. But anyway, I'll do it for you. So we know that when there's 4 bits is 0 to 15. So we know that this would be 15. We know our decimal point is on. And for our whole number part of the deal, hopefully you can see that's a 5. So now we've just represented decimal numbers with light bulbs. Because if you remember, we could just have these 9 light bulbs stacked together. We tell our eye that this one is a decimal number, and we can do whatever we want. We could also naturally do it a 10-bit system and even add a bit here to say plus or minus. So you've seen how we can play with bits and get decimal numbers, any number, negative and positive numbers. But then, wasn't this video about AI? How do we connect back to words, to letters? How could that be? Well, we can build from our system. So let's assume a 2-bit system. What does 2-bit mean? Yeah, exactly. We have 2 houses. Let's assume all of them are off. My first one is on. My second one is on, and all of them are on. And now we have our eye here looking at these numbers, right? Looking at our configuration of 2 light bulbs every second. So of course for us, we deal with numbers. This is 0, this is 1, this is 2, this is 3. And we can tell the eye that this light bulb configuration represents the letter A. We map a number to a letter. So we say that 0 is A. We say that 1 is B. We say that 2 is C. And we say that 3 is D. If I wanted to spell cab, I'll let you try it for a second before I do it. I would just have to tell my eye, I would have to flash them in order. I'll see here letter C. It's my number 2, and my number 2 is like this. And then I see that my letter A is all of them off. So I give them all of them off. And then I see that my 1 represents B. So we can see here that this represents cab, just by flashing our light bulbs. Of course, I'll do one more word. Let's say we want to say bad. Using our system here, we can see that this is 103. And if we wanted to draw for our eye what this means, we will just do here B is 1, so it's 0, 1, A 0, 0, and then we make our D here. Bad. And this exists. This is, in our computing, engineers, very smart people, got together and they made a standard for it. One of the initial standards is the ASCII table. But this was only for the English language. And as we expanded and went more global, there's starting to be the need for better mappings of letters and numbers. A very common one now is UTF-8. And what does the 8 mean? It means it's an 8-bit system or a 1-byte system, which means it has how many different values? I'll let you guess, but it means that each letter is represented by 8 bits. So I'll let you calculate how much that is because it's already been done and I want you to work on it. So to recap, I hope, dear viewer, that you fully understand how binary numbers work. You can see with what we like to say an electrical wire sending pulses or signals at a moment and having something or a catcher of some sorts checking if the wire is on or off or if the light bulb is flashing or not. And if we stack a lot of light bulbs together, that each position of this light bulb matters for our eye, that we can start representing any number in existence as long as you keep adding light bulbs, and that if we map numbers to letters, that we can write any word in any language via our computer or via electrical signals. I hope that you can see that the rocks that makes the live wire, the statement that ones and zeros is how computers talk and everything is ones and zeros, it's very clear for you and you understand now how binary numbers work. So thank you for watching. I hope you learned something. I hope you're better than yesterday today. And if you want to keep improving yourself and learning more, like and subscribe. Give me any feedback you have, and I'll see you in the next video.